Next on our agenda are the autoregressive models. A stationary stochastic process YT is said to follow an autoregressive model of order 1 if it satisfies this model equation, where YT is regressed on a constant mu and its own past value, hence the name autoregression. More generally, for an autoregressive model of order P, YT is regressed on its own past values up until P periods back in time. Again, it is a good refresher to verify the properties of AR models, such as given over here for an AR1 process. As you can see on the slide, the autocorrelation of an AR model at lag K is given by the kth power of the AR parameter. Hence, the theoretical parallelogram of an AR1 model looks like this. All autocorrelations are different from zero, but they slowly decay. And so autoregressive models show much more persistency than moving average models. This also means that, unfortunately, the parallelogram is not a useful tool to specify an appropriate AR model, as we could not distinguish it from a high-order moving average model. So we need to rely on a second tool to specify appropriate AR models, and that is the so-called partial parallelogram. Now, the partial parallelogram uses partial autocorrelations. And what are these? Well, the partial autocorrelation, or just in short, the partial correlation at lag K, looks at the correlation between y at time point t and y at time point t minus k, conditional on, so holding fixed all observations in between. Intuitively, this is the correlation between yt and yt minus k that is left after filtering out the effect of all other observations that fall in between. To get a better grasp of these partial correlations for the AR1 process, let's have a look at this figure. At the top, I visualize the time series process YT. At the bottom, the error process epsilon t. Now, keep the model equation of an AR1 model in mind. And so then you will see that YT is directly influenced by YT minus 1, which I indicate through this error, as well as by the error process at the same time point P. Likewise, YT minus 1 is directly influenced by YT minus 2 and the error at the same time point T. Now, what would be the partial correlation at lag 1? Well, there are no time points in between to condition on. So that is simply the autocorrelation at lag 1. So as of lag 2, things start to differ. What is the regular autocorrelation at lag 2? Well, that is non-zero, since there is a path from YT minus 2 to YT, namely over YT minus 1. But what would be the partial correlation at lag 2? That would be the correlation between YT minus 2 and YT, when YT minus 1, so the guy in the middle, needs to be kept fixed, so can't move. If YT minus 1 needs to be kept fixed, then changing YT minus 2 will not lead to a change in YT, since there is no other path from YT minus 2 to YT than the one over YT minus 1. So the autocorrelation at lag 2 is 0. In fact, if we would be making the partial parallelogram of an AR1 process, we would be getting something like this. Note, very confusingly, that in R, the partial parallelogram starts at lag 1, so not at lag 0, as was the case for the parallelogram. So don't make mistakes on this in R. What do we see? Well, for an AR1 process, we see here that the first partial autocorrelation is significant. But as of them, they implode, they become insignificant. So the partial parallelogram is a useful tool to specify the order of AR models. Look for the lag as of which they vanish, they implode, and take this as a sign to specify the order of an AR model. Now, one aspect I have been ignoring until now is the very important stability condition for an AR parameter. In the assignment, you also saw this popping up over here, the condition that phi needs to be smaller than 1 in absolute value, which is a stability condition. Why is this needed? Well, later on in the course, we will see that there is an important distinction between the stationary world and the non-stationary world related to this AR1 parameter. If phi is smaller than 1 in absolute value, then we have a stationary AR process, and shocks to our series have only a temporary effect. But if the absolute value of phi is equal to or larger than 1, shocks have a permanent or an even explosive effect. Now, where does this stability condition come from? Well, let's start from the model equation of an AR1 model, which is given over here on the slide. Now, the model equation holds at any time point t. So let's plug in the model equation for time t minus 1, which I do over here in parentheses. Now, by recursively doing this, so again, by plugging in the model equation for yt minus 2 and so on, we obtain this expression where we have a sum of constant terms, a sum with all of the lagged error terms, and we have our initial condition denoted as y not popping up, since we need to initialize our process somewhere. If we would now let the sample size go to infinity, we see that the influence of this initial condition only dies out if phi, so phi1 is smaller than 1 in absolute value. Also, past shocks would only have a temporary effect. If, on the other hand, phi would be equal to 1 or larger than 1, then the opposite occurs. Now, under this stability condition, the solution would further simplify to this expression over here, where we get a constant term and the infinite sum of all past errors. But this is a model equation that reminds us of the one for moving average models, namely with infinitely many moving average terms included. And it is indeed the case that an AR model can be rewritten in terms of its moving average representation, where the MA parameters are given by the powers of the AR1 parameter. Now, from this, we've learned that it is important to verify that the phi parameter satisfies the stability requirement for an AR model to be stationary. But can we also verify this easily for an AR2 model? Well, you can start from the model equation and do recursive substitution, but I think you will quickly find out that there is no easy pattern that emerges. The question then is whether it is also possible to write our process as an NA infinity. And the answer to that question is yes. And to do that, we will make use of a convenient trick, which is writing out the AR model in a companion form, where we actually write out the process, so in general, an ARP process, in terms of an AR1 form. Why do we do that? Well, we write it in an AR1 form since we know how to obtain the moving average infinity representation from an AR1 representation. How can we obtain this companion form? Well, by writing down a system of P equations. The first equation is for yt, and below we stack its P minus 1 previous observations. To arrive at an AR1 representation, we would need to have this vector over here, denoted by xit, popping up at the right-hand side with its lagged value, so xit minus 1. And this is also what you see happening. The first entry becomes yt minus 1, second yt minus 2, and so on. Now the P by P matrix F needs to be filled in such a way that we retrieve from this system of equations our ARP model equation. And this can be seen from the first line, where yt is nothing more than phi1 times yt minus 2, plus phi2 times yt minus 2, and so on, all the way up until the end. And don't forget the error term, which we collect over here. So the first equation gives you the model equation of the ARP process. The other equation in our system of P equations are just meant for matching the lagged values of yt that pop up at both the left-hand side and the right-hand side. So we simply need to match them up. Yt is nothing more, yt minus 1 is nothing more than the first entry over here. Yt minus 2 is the second entry over here, and so on. So this gives rise to our matrix in our companion form. And we are ready to write out the AR1 model equation in this companion form. Yt is the first component of our vector xit, which I have extract over here with this vector. And xit follows an AR1 model equation, which can be rewritten through recursive substitution like we did before. And here again, our initial condition pops up. And what would we want? Well, like before, but now in matrix notation, we would want the f to the power t to become small for our infinite sum to arise. Now one can show that if all eigenvalues of this matrix F are within the unit circle, then the autoregression is stable. So if all eigenvalues are smaller than 1 in absolute value, we have a stable process. Why do we talk about a unit circle? Well, some of these eigenvalues can actually be complex. Now, how can you obtain the eigenvalues of a matrix? Well, by solving this equation given here on the slides. Don't worry, I will only ask you to compute this determinant over here for 2 by 2 matrices. So no need to worry for larger dimensions. Alternatively, this proposition in Hamilton tells you that you can immediately write down this p-th order polynomial and solve for its roots, which need to be within the unit circle for our process to be stable. In your tutorial assignment, you will actually be asked to verify this stability condition for a simple AR2. Before we continue with ARMA models, one final remark on stability. In some textbooks, you will see another requirement popping up that certain roots of a characteristic equation need to lie outside of the unit circle, so not inside. Not to raise any confusion, I'm including this alternative requirement here on the slide, such that you are aware of both versions. This alternative way of checking stability starts from writing the AR model in lag operator notation, where we make use of the lag operator L which operates on a time series and returns another time series, namely its lagged version. The lag operator is defined formally over here. If we work this out for the first equation, we indeed see that we get here yt for the first term, and then phi times the lag operator operating on yt, so yt minus 1, and so on. And this is nothing more than our ARP model equation when you bring all of these terms to the right-hand side. Equivalently, you can then check the stability of your model by searching for the roots of this polynomial equation, which should then lie outside of the unit circle for our process to be stable, since the z popping up over here is nothing more than the inverse of lambda from the previous slide.